Uniform circular motion. When an object travels in a circle at a constant speed, it's accelerating, and the direction of its acceleration is inward, and its value is given by the equation v squared over r, where v is the speed of the object and r is the radius of the circle. Now, from Newton's second law, we know that a net force causes an acceleration. And since the net force is always in the same direction as the acceleration, the net force is also center directed. So using Newton's second law and combining it with this expression for the centripetal acceleration, we get that centripetal force, which is that net force center directed, is equal to m times AC, which is v squared over r. So these two equations are handy equations in this unit. Now, when an object travels in a circle, we can find its speed using distance, which in the case of a circle is the circumference, 2 pi r, divided by the period. Now, if I combine this equation with this equation, I get an expression for the centripetal force in terms of the radius of the circle, the mass, and the period. That is the time for the object to go around the circle once. So we get Fc is equal to m 4 pi squared r all over the period squared. Now, suppose we have a car that's traveling in a circle, and we want to draw a free body diagram of it. Okay, so let me erase this. Okay, so I'm going to show a front view of the car. And it's going around a corner. This is the center of the circle. Radius is r. And let's say the car is traveling at a speed v, okay, which at this moment is directed out of the board. Now, drawing a free body diagram, we have the weight of the car, acts straight down. We have the normal force, straight upward. And since the car is rounding a corner, there has to be a net force acting on it, which is to the right from this viewpoint. And the only thing that could provide that force is friction. So let's say the car is not slipping, but it's on the verge of slipping, so we have the maximum force of static friction. And guess what? That is what provides the necessary centripetal force to allow the car to round the corner. So we have Fs max then, we can set equal to m v squared over r. Right? This is really from Newton's second law. This is the centripetal force, and v squared over r is the centripetal acceleration. Now, the maximum force of static friction we learned earlier in the course is equal to the coefficient of static friction multiplied by the normal force on the car. But since the car is not accelerating vertically, isn't the normal force equal to the weight of the car? And from Newton's second law, again, isn't the weight of an object equal to the mass of the object times the acceleration due to gravity? Now notice that mass appears on both sides of the equation sign, so the mass cancels. And now we could solve for whatever. Let's solve for v. So we get v is equal to the square root of the coefficient of static friction times the acceleration due to gravity times the radius of the circle. So that is the maximum speed that a car can round this corner, where the coefficient of static friction is known, the acceleration due to gravity is known, and the radius of the circle. Now suppose that the curve is banked, and what we're going to do here is just to figure out if we can bank this corner so that the car doesn't need friction to get around the corner. Okay, so we have a banked corner. Okay, here's our car. If we draw a free body diagram, we have the weight down, and and we have the normal force perpendicular to the surface upon which the car is setting. We have the angle of the bank. Now, if this is the center of the circle here, and this is the radius, okay, don't we need a center-directed force toward the center of the circle? And the only thing that can provide that, since we don't want friction, is a component of the normal force which is parallel to the ground. And I'm going to call that Fnx because that's going to be my x-axis. And then that leaves us with the component Fny, which has to be equal to the weight. Okay, let me just shorten the weight vector here. Okay, so these two vectors are equal, right? Because the car is not accelerating vertically. So Fny must be equal to the weight. So, using Newton's second law, we can write that Fnx is equal to the mass of the car times the acceleration of the car, which would be v squared over r. Right, where v is the speed of the car, and at this moment it's directed out of the board. Now, Fnx, okay, Fnx would be equal to the normal force times the sine of the bank, the angle of the bank turn. That's equal to mv squared over r. Now, Fny has to be equal to the weight of the car because the car is not accelerating vertically. And Fny would be Fn times the cosine of the angle of the bank corner. From Newton's second law, the weight of the car is equal to mg. Now, if I combine these two equations, I'm going to solve this for Fn. And then I'm going to substitute this expression into this expression. And I get mg tangent of theta is equal to mv squared over r. Now notice that the mass cancels. And let's say I want to solve for the angle. So I have theta is equal to the arctan of v squared over rg. So this tells us the angle at which this corner has to be banked so that the car can get around the corner at this speed without the need for friction. All right, now let's take a look at an airplane going around a corner, okay, cornering. Well, it turns out that an airplane does have to bank itself in order to go around a corner. And the reason for that is because if you draw a free body diagram, you can see that the weight is down, but the lift is always perpendicular to the wing. So the only way you can get a horizontal force pointing toward the center of the circular path that the airplane is flying in is if the airplane is banked. So we have here that the lift in the x is actually providing the centripetal force. So we can set Lx equal to the mass of the plane times the speed of the plane squared over r. And that leaves us with Ly, which is equal to the weight. You notice that this is very similar to the bank corner problem for a car. So we have Lx is equal to mv squared over r. And I'm going to call this angle theta. So Lx is L sine theta. That's equal to mv squared over r. We know that Ly is equal to the weight, which is mg, and Ly is L cosine theta. Solving for L, we get mg over cosine theta. Substituting into here, we get the tangent of theta times mg equals mv squared over r. The m's cancel. So we have tangent of theta times g is equal to v squared over r. So now we can solve that for whatever we want. We could solve it for the angle at which the plane has to put itself. We can solve for the necessary speed to go around this corner. We can solve for the radius, whatever. Okay, so that's an airplane flying around a circular path, or flying on a circular path. All right, next let's take a look at an amusement park ride called the rotor ride. Now the rotor ride is a cylindrical room, okay, that's spinning about this central axis, and the riders inside feel like they're being pushed against the wall of the ride. Now really what's going on, if you look at this from a top view, okay, here's a rider. This rider wants to go on a straight line path, but the wall of the ride is getting in the rider's way. So it's the wall that's always exerting an inward force on the rider, and so that provides the necessary centripetal force to keep the rider on a circular path. So if I draw a free body diagram here, we have Fn, because the wall is exerting force inward on the rider. It's like the support force, like when you're standing, you have that normal force upward. So here you have the wall exerting a perpendicular force inward. We call that the normal force. We also have the weight of the rider down. And there has to be a force upward. The only thing that can provide that is another electric force, and it so happens to be friction. Let's say that the person is on the verge of slipping, so we're going to make this the maximum force of static friction. All right, so I can set Fn then equal to the mass of the person times the speed of the person squared over the radius of the circle. Okay, so R is here. At this moment, the person is coming out of the board. The normal force we can relate to the force of static friction. Okay, using the equation, maximum force of static friction divided by coefficient of static friction. Okay, so that's the normal force. So that's equal to mv squared over r. And we know that since the rider isn't sliding downward or accelerating downward, that the maximum force of static friction is equal to the weight. So I can rewrite this as weight over coefficient of static friction is equal to mv squared over r. From Newton's second law, the weight of the person is equal to mg. Notice that the mass of the person cancels out. So now we have an expression g over mu s is equal to v squared over r. And we can solve that for whatever we want to find. Okay, let's apply now uniform circular motion to a satellite going around the Earth. Okay, so this will represent the Earth, mass me. Earth has a radius re. Okay, here's our satellite, which let's say is at an altitude h. Satellite's traveling at a speed v. Now, there's a gravitational force on the satellite, which has a mass m. And that gravitational force is what provides the necessary centripetal force to allow the satellite to follow a circular path around the Earth. Well, isn't the gravitational force then equal to the mass of the satellite multiplied by the mass of the Earth divided by the center-to-center distance between the Earth and the satellite? So that would just be re plus h squared. And then we have to multiply by the universal gravitation constant. But isn't the force of gravity also equal to the mass of the satellite times the speed of the satellite squared divided by the center-to-center distance? So we can write this as mv squared over re plus h. Now, the mass of the satellite cancels. Let's bring in an equation for speed. Right? The speed of the satellite is equal to the distance over time, or the circumference of the circle, divided by the period, which is the time to go around once. So we have v is equal to 2 pi times re plus h divided by the period. Okay, substituting that into this expression, I get 4 pi squared re plus h all over the period squared. So that's equal to the universal gravitation constant times the mass of the satellite times the mass of the Earth all over RE plus H squared. Okay, multiplying both sides by RE plus H squared, I have 4 pi squared RE plus H cubed is equal to G ME of the mass of the satellite canceled out, so I want to take that away. And then this side is divided by the period squared. If I multiply both sides by period squared and both sides by 1 over 4 pi squared, I get RE plus H cubed is equal to G ME over 4 pi squared times the period squared. And this is actually known as Kepler's third law. It says that the square of the time it takes a planet to go around the sun, or in this case a satellite to go around the Earth, is proportional to the cube of the center-to-center distance between the satellite and the Earth, or a planet and the sun.